And let's continue on functions and then graphs. So I'm going to move on to section 1.8. It's on the composition of the composite functions, meaning combination of functions. So we're going to combine different functions together to create a new function. Combination of functions. We have arithmetic combination and then composite functions. So two major categories: arithmetic combination. Second major category is composite functions. And let's get to the learning objectives. So we learn how to add, subtract, adding, subtracting, multiplying, dividing the functions. And those four basic operations actually is the foundation for the arithmetic combination. We'll learn how to find a composition of one function with another function. Then we use the combinations and then compositions of function to model and solve real-life problems. Let's start with the arithmetic combinations of functions. So again, we're dealing with adding, subtracting, multiplying, and divide functions. Okay, let's start with the just as two real numbers could be combined by the operation of addition, subtraction, multiplication, division to form other real numbers, two functions could be combined to create new functions as well. So we start with addition, sum, addition, difference, product, quotient of two functions f and g. So let's say f of x equal 2x plus 3, 2x minus 3, g of x equal x squared minus 1. So if you combine two functions, adding them, so just do 2x minus 3, adding x squared minus 1. Okay. Put into the parentheses and then get rid of parentheses. Since it's addition, we keep everything as it is. Adding x squared minus 1, combine like terms, end up with x squared plus 2x minus 3 minus 1, combine them, you get minus 4. Then we put the terms in the decreasing order, start with the highest power, then gradually move down to the constant. So that's addition, we have subtraction as well, so 2x minus 3 minus x squared minus 1. So right here we simplify the expression, so we get 2x minus 3, distributing negative 1 here. If you want to put back the invisible 1, distribute it, you can do that. Negative 1 times x squared is minus x squared. Negative 1 times negative 1 is positive 1. Now again, we're keeping the decreasing order, start with the negative x squared, then we move down to the constant linear term 2x. Combine those two constants, minus 3 plus 1, 1 minus 3 is minus 2. Okay. So come out with the difference of two functions. The third one is multiply both functions, multiplication, so do 2x minus 3 times x squared minus 1. And again we distribute it, FOIL this, FOIL this expression, 2x times x squared gives us 2x cubed. 2x times negative 1 is minus 2x. Minus 3 times x squared is minus 3x squared. Negative 3 times negative 1 is positive 3. Now again, we're going to put into the decreasing order based on the variable x. Let's start with 2x cubed. And then minus 3x squared minus 2x, adding 3. and that becomes the product of those two functions. And the quotient just basically put f of x on top, g of x on the bottom, you get a quotient of those. And then we cannot simplify this quotient, but only one thing is when you create a new function, you want to make sure it's defined. So here, when x squared minus 1 equal to 0, then the function is undefined, so we need to eliminate those undefined points, undefined numbers from the domain. Right here we have perfect square adding 1 from both sides of the equation. X squared equal to 1. Then after that we're taking radical x equal to plus minus radical 1. And this is plus minus 1. And that's why here we excluding plus minus 1 from the domain. So domain for the new function, which is a quotient of f of x and g of x, turn out to be all real numbers except plus minus 1. Okay. And the domain of an arithmetic combination of functions f and g consists of all real numbers that are common to both domain of f and g. It's like the common meaning intercept, right? So you're looking for the intercept of domains satisfying both f of x and g of x. In the case of quotient f of x over g of x, that's the further restriction that g of x cannot be equal to 0. We want to make sure the function is defined, so we eliminate those x values that makes the function undefined. So we have sum, difference, product, quotient of functions that f and g be two functions with overlapping domains, and for all x common to both domains, the sum, difference, product, and the quotient of f and g are defined as follows. The sum f plus g parentheses to the x, just sum up those two functions, f of x plus g of x, and difference f minus g parentheses of x is basically equal to f of x minus g of x, f times g parentheses of x equal to f of x times g of x, the product. The quotient f over g parentheses of x, f of x over g of x. And here g of x cannot be 0. And you can also sometimes you also see these people do skip. Just write f plus g, right? So you know that it's f plus g. Function f plus g. F minus g is function f minus function g. F times g becomes f times g. And this is regular notation, and this is function notation. Left is the function notation. On the right is a standard notation. F over g, just basically f over g. Okay. And to put into a simple expression, you can do that. So now given f of x equal 2x plus 1 and g of x equal x squared plus 2x minus 1, let's find f plus g of x, meaning sum up those two functions, then evaluate the sum when x equal to 3. So here we have f plus g of x. Basically it's adding f of x to g of x. And we just throw in f of x here, throw in g of x here. F of x is 2x plus 1, g of x adding x squared plus 2x minus 1. And after that we combine like terms. By the leading term here, it's x squared, 2x plus 2x gives us 4x, plus 1 minus 1 becomes 0. Okay, so and basically you can omit that. So we get a new function. The sum of those two functions turn out to be x squared plus 4x. Now this is combination of those two functions. Now f plus g of 3, or x value equal 3. Now we go back to the combination of functions, replace x with 3. So whenever we see x, it becomes 3. So this becomes 3 squared plus 4 times 3. 3 squared is 9. 4 times 3, that turned out to be 12. 9 plus 12 is 21. So we get a concrete result, 21. Now let's look at the composition of functions. So we combine two different functions. We using composed f composed g or g composed f. Another way of combining two functions to form a composition of one with another. For example, let's say f of x equal to x squared, g of x equal to x plus 1. The composition of f with g is written as f of g of x. And right here, we make it simpler. So main function is f. So now replace g of x with x plus 1. So you get f of x plus 1. Here we just replace g of x with given expression x plus 1. Now we go back to the function f of x. Now instead of using variable x, we're using variable x plus 1. So go back here, x value now becomes x plus 1. So it becomes x plus 1 parentheses square. And this is what we call a composition of those two functions. And you can write it as f composite composed with g, right? F with a little circle in between g, read as f composed with g. And we can also do g composed f. So g of f of x. Okay. G composed f. G function g is the main function. Now replace f of x with x squared first. Now go back to g of x. Whenever you see x, it becomes x squared. So we get x squared, x becomes x squared, adding 1. Okay. And this is f composite g, composed with g. Second one is g composed with f. Okay. Whichever you write first, that's what we call the main function, and then the second function is what we call inner function. So outer function, inner function. This is outer function, and this is inner function. And that make a difference, outer function. Whichever appears first is outer function, and appears second, that will be the inner function. The composition of function f with the function g is f composed with g of x. So it's equal to f of g of x. And the domain of f composed with g is a set of all x values in the domain of g, such that g of x is in the domain of f. Meaning basically you want to satisfy both function g and then function f at the same time. This diagram just show you the essence of the domain for composite functions. Okay, so let's look at an example. Given f of x equal to x plus 2, g of x equal to 4 minus x squared. Let's find the following f composite of g. So again, this is f of g of x. So simply you just rewrite it as function notation. Then we know g of x, it turned out to be, that's inner function, so it's 4 minus x squared. And then function f is outer function. Now we go back to the f of x and replace x with whatever inside parentheses inner function. So x becomes 4 minus x squared. So it's 4 minus x squared adding 2. Now again, we combine the constant. So writing the variable term first in the decreasing order and adding a constant. So negative x squared plus 6. That turned out to be the composition of F composite of G. Okay. And the second one, we're going to do a G composite of F. Okay, we're going to do it together here. G composite of F. We're going to write it as G of f of x. And again, replace f of x with x plus 2. That's inner function. The outer function g of x. Now go back to outer function. Whenever we see the x, it becomes x plus 2. So you get 4 minus x plus 2 squared. And this is 4 minus the perfect square turned out to be x squared plus 2 times x, adding 2 squared. Okay, then simplify a little bit. So 4 minus x squared plus 4x, adding 4. Now expand it, combine the like terms. It's 4 minus x squared, distribute negative sign to every single one of this. Return everything inside parentheses to negative. Minus 1 times plus 4x minus 4x. Negative 1 times positive 4 is minus 4. Now these two constants cancel each other. We end up with negative x squared minus 4x as the composition of G and F. And since we know this composition function G of composite f of x, this turned out to be negative x squared minus 4x. So all we have to do is replacing x here with negative 2. Okay. So it become x becomes negative 2, so it's negative 2 squared minus 4 times negative 2. Negative 2 squared is positive 4, so this is minus 4. Carry over the negative sign. And negative 4 times negative 2 becomes positive 8. We're adding those two constants together, it turns out to be positive 4. Okay. So result for G composite F composed with F of negative 2 becomes 4. And you can try on your own. So in the previous example, you form a composition of two given functions. In calculus, it's usually very important to decompose the function, which makes up a given composite function. So for instance, let's say we have a function h of x equal to 3x minus 5 to the third power. And here the outer function should be something cube. So outer function is x cubed. So some variable to third power. G of x is inner function 3x minus 5. So h of x is composition of those two. And we can say that it's f composite of G. So f composite of G becomes f of G of x. So to decompose a composite function, look for the inner function and the outer function. Okay. To inner function is whatever inside parentheses. Outer function will be the main function. Here G of x equal 3x minus 5 is inner function. F of x equal to x cubed is the outer function. Now let's take a look at application. The number n of bacteria in a refrigerated food is given by n of t equal to 20t squared minus 80t, adding 500. T is greater equal to 2, less equal to 14, and T here is the temperature of the food in degrees Celsius. When the food is removed from refrigeration, the temperature of food is given by T of t equal to 4 times time t plus 2. So here t is greater equal to 0, less equal to 3, where t is the time in hours. And first of all, we want to find the composition of capital letter N composed with a capital letter of t, and I interpret the meaning, find in a real context, and probably find the time when the bacterial count reaches 2000. So first of all, let's rewrite the n of t is 20t squared minus 80t, adding 500. And T of t is 4t plus 2. Now we're going to do the composite of capital NT over of the T of t. So right here, so NT is the outer function, T of t is the inner function. T of t turned out to be 4t adding 2. So here, then go back to the outer function, our main function, nt. Now replace t with a 4t plus 2. Square that, minus 80, 4t plus 2, and adding 500. And first of all, we get 20, let's expand the perfect square here. 4t parentheses square becomes 16t square. And then twice of 4t times 2 is 16t. Adding 2 squared turns out to be 4. We're going to distribute the second parentheses. Minus 80 times 4t is minus 320t. Minus 80 times positive 2 is minus 160, adding 500. Now we distribute it. 20 times 16t squared is 320t squared, adding 320t, adding 80, minus 320t, minus 160, adding 500. Now the constant term the linear term get cancelled. We combine all these constant, so we get 320t squared. 80 plus 500, 580 minus 160 is 420, positive 420. Okay, so this function represents the count of bacteria in the refrigerated food. Okay, the number of bacteria we are looking at as a function of the time t. Okay. Now, second part is when the bacteria count reach 2000. So meaning we're setting n of t of t equal to 2000. We already have the n composite of nt with the t of t, and that's 320t squared plus 420. Then you set that equal to 2000, and you solve for t. First of all, subtracting 420 from both sides of the equation, and it turned out to be 320t squared equal to 1580. And we dividing 320 from both sides of the equation. Cancel that, t squared equal to 4.9375. You're taking the radical on both sides of the equation. Yeah, well, 1580 by 320 turned out to be 4.9375. And now, next step, taking the radical on both sides of the equation, t equal to plus minus radical 4.9375. And this turned out to be approximately plus minus 2.2. And we're looking at the time, so time t cannot be negative. So that's why we end up with the only answer, which is t approximately equal to 2.2 hours. At time, there's no negative time. So that's why negative values is not applicable here. So basically we eliminate that. Yep. So that's pretty